Thank you. Okay, let's quickly recall the notation that we had in Stefan's talk, which I will be using again. So let me just write it. So K is it's a little bit small. I'm sorry, I started writing a little bit bigger. Is a complete discrete valuation field of characteristic 0, and O is the discrete valuation ring. So we know the residue field by K bar, and it's supposed to be algebraically closed of characteristic P. Okay, then we have V, the valuation, etc. M, the maximal ideal. Okay. And so now suppose, so what I want to do in this talk, so we've seen the main question that we want to study is given a Galois cover in characteristic P, can we lift it to characteristic 0? And already Stefan in his talk this morning told you that, well, if we just start with any, suppose that we can lift it and we try to reduce it back, then sometimes we see that, okay, that it can never be the thing that we started with, so the thing could not be lifted in characteristic 0 to characteristic 0. So it's a problem that we want to study a little bit more in detail in this talk. Yeah. Okay. So so in this talk we suppose that we start with a curve y over little k, so over the field of characteristic 0, together with a finite group of automorphism. Or what amounts, of course, to the same. We have a G-Galois cover in characteristic 0, and now we just try to reduce it to characteristic P and see what comes out, and then this gives us hopefully some information on which covers we can at all come from characteristic 0. Okay. So we denote by y1 up to yr the ramification points of this cover. Maybe we call the cover F. Okay. So now I first want to tell you what I mean by reduction. What's the kind of thing that we want to look at? So first, this actually we have already seen in Stefan's talk. So a model of the curve y over the discrete valuation ring O will be denoted by curly y, and this is supposed to be a curve which is normal, flat, and proper over O, of course, such that if I tensor it with my fraction field k, then this should be just the curve we started with. And now such a model is called G semi-stable if the following condition holds. So okay, now I look at the reduction of this model, so the characteristic P fiber, y bar, and this should satisfy the following condition. It has the singularities are at most ordinary double points. And okay, this is this semi-stable. The G semi-stable means that the G action extends to the model. And then there is a further condition that these ramification points, yi, they specialize to pairwise distinct smooth points. I'm sorry, I wrote a bit too much on this page. I will improve this. Okay, so they should specialize to pairwise distinct smooth points. Okay, and okay, so if we have such a thing, because the G action extends to Y, we can we can take the quotient from y with respect to g, and that gives us again a finite flat map, and one can show that this quotient curve x, curly x, is again semi-stable. Okay, so this means just the first part of the definition, that it only has ordinary, the special fiber has only ordinary double point singularities. Okay, so we have, well, we call it maybe f sub o. This is a finite map, finite flat map between semi-stable curves. And moreover, so if this this number, the Euler characteristic, basically almost, so it's the 2 times the genus of the curve we started with plus the number of ramification points, which are called r, minus 2. If this is positive, then there exists a unique minimal G-stable model, a G semi-stable model, and this is then called G-stable. Well, it's not quite true the way I write it here. For this minimal model to exist, we may have to extend our field K by a finite. So after replacing K by a finite extension. But as Stefan already told you in his talk this morning, we are always allowed to pass to a finite extension without actually mentioning. For our problem, it's not so important. So this is not so bad. This is not so, for us, we don't really care so much. So it means that there is the curve may not have good reduction. It may not be a smooth model, but at least this is at the best we can do, having this very mild type of singularities. Okay, let's just since this is so important for what follows, let's just look at 2 examples. Okay, first example, take p equal to 2 and k equal to, so I take the maximal unramified extension of the 2 adic numbers, but I need, for this example to work, I need to add a 4th root of unity. And then, okay, so we look at a very simple curve with in characteristic 0. This is a curve of genus 2. Call this polynomial G. And the map I look, it's also very easy. I just look at the projection on the x coordinate, just the projection on the 2-to-1 map to the P1. Okay, then this equation, if we just take this equation, this already defines as a model of a curve y. Because, well, what can we do? We just take for y the curve over O, which is given by the same equation. So this defines, this star, it defines as such a model y0 to x0, also of the curve, right? Given by exactly the same equation. That's what's supposed to mean this. So now if we look at the special fiber, so we reduce now this equation modulo 2, apply the Jacobi criterion, and you immediately see that this is singular in the point x equal to 1. Well, it's really very easy. You just take the derivative. This is a 4th power, so the derivative is 0, and this is just x to the minus 1 to the power 4. So you immediately see, okay, this was not, and this is a very bad singularity in this one point. So we get, this is just the normalization of this curve is a projective line with a bad singularity in one point. This is definitely not the model, the G-stable model that we are looking at. So what do? Well, we have to blow up this curve y in this singularity. Okay, so while blowing up and finding exactly which blowing up you have to take, this actually it's not so easy in general. And this could be a whole talk on itself, so I'm not really explaining how to do it. The details of this example are in the notes. But I just want to give you a few ideas on it works. And we have seen in Stefan's talk that the key point here is just seeing what happens to the branch point. So the branch points of this cover here, there are 6 branch points, just 0, x is 0, infinity, and plus minus 1, plus minus I. And so the key point of studying this example is just really seeing what happens to these 4 points in characteristic 0. So let me just quickly, as this is the reduction x0 bar. Yeah, so this is the generic, this is supposed to be the generic fiber. And so here we have these 6 branch points. Yeah. So we have 0 and infinity, they specialize to distinct points on the special fiber, but all the other points, they specialize to 1. Yeah. Reducing just this point. And so now what you have to do to analyze this this stable reduction of the cover is, well, you just have to compute the p-adic valuation of the difference of all the 6 points. And if you do that, then you see actually what happens. So if you just want to say, the first thing we want to do is to separate these branch points. Yeah? So how do you have to do it? Well, you just have to look what is the difference between the valuation of the difference, exactly like Stefan did in the example that he had at the end of his talk. And so, I mean, now I'm just drawing the thing in positive characteristic. Just draw it. Yeah. And so if you compute the difference between the valuation of the difference of these points, you see that there's a different, there's the 6 points that form 3 pairs. Okay, and this is what this, if you just to separate these 6 points on the projective line, one has to blow up here in this point, the P1 over O in this point several times, so that in the end you get these 4 components. And the component that interests us now in this talk mostly is this, the bone of the COM, so to say, this the component which I call x2 bar, and the blow up that this corresponds to the coordinate change x, substituting x as the square root of 2, x2 plus 1. So if you now consider the x2 in characteristic 0, it also defines a coordinate on your projective line. And now if I rewrite this equation in terms of this coordinate and you reduce then everything modulo p, then you see that 0 and infinity, they reduce to 1.1, and minus 1 reduce to 1 point, and so on. Okay, so what we can do, we can consider now the projective line over O with coordinate x2. Call it x2. And now what we can do, we can define a model of y just to be the normalization of x2 in the function field of y. This defines a model of y. And what you can show, I mean, I'm not going to do the calculation here because so you can show that if I now look at the special fiber of this, it's given by the equation which I'm now going to write down. Of course, if you look at this, this is still an inseparable map of this projective line x2 bar, and well, this is still singular. I mean, so really what I did is I took the normalization of the thing in mixed characteristic and then reduced. Because otherwise, if I would take normalization in characteristic P, this is not normal. I would never have gotten this. But this is exactly what you get if you do this computation. And now if you apply the Jacobi criterion, you find that this has 2 singularities. Yeah? It's just, I mean, it's just the 2 zeros here of this part here. These are the 2 singularities now. It's different from before. And so what this means, this is the picture, but now on y. So this is now the picture of this y2, like this, the reduction of this one. This is this picture that we had before with here this component y2. And here it is two singularities. So to get the stable model of our curve y, we, oh, I'm sorry. So if we now to get a stable model of our y, we have to blow up at least this model y2 in these 2 points. And if you do that, the fact that it's a singularity, it means that there should be a component of positive genus. And since we only have genus 2 on the generic fiber, it turns also out that you can actually compute these things. These are really then elliptic curves. And of course, so it means this discover that we studied, it has bad reduction. Okay. And so this is the picture now of the reduction of this G-stable model. So we have separated the points here. This was the first step that we did. And we have found the components of positive genus. Now, very quickly, a second example. Okay. So this time P is an odd prime, different from 3. And I look at the Kummer equation. Yeah. So A is some parameter, which now afterwards we're going to choose it. So it's I consider the degree P map just mapping x and y to x, projecting onto the coordinate x. This is a Kummer equation of degree P. And of course, if we take, just as before, the model given by this equation star here, just taking exact same formula, then we get, of course, a model which is not semi-stable. And if we look at the singularities, special fiber, y by 0, they're of course given by the zeros of the derivative of this polynomial g. So the solutions of this equation, 3x squared minus a is 0. So we have 2 cases. The case A is if this A, yeah, it's if this, I suppose it's a number in K. If it's not, if it doesn't reduce to 0 modulo P, then there is 2 singularities. And just as before in the previous example, so as soon as we have 2 singularities, blowing up will lead to some component of positive genus somewhere there. Maybe more complicated than the example I showed you, but there will be a component of positive genus. And so it certainly has bad reduction. And then one can check. If I choose, for example, P, A equal to P, then you see that this has only 1 singularity. And one can show this is actually by doing the same kind of trick that Stefan did in his talks. I'm not going to write it down now, but it's exactly the same kind of computation that Stefan did in his talk. We see that in this case we have actually good reduction. And the picture, in this case, it looks as follows. So here we have this component y by y0 bar, which separates the 4 points. And here we have another component which we gotten by blowing up this model y in the singularity. So in this case, it's this x is 0. And that yields here, in this case, such an Artin-Schreier equation. Maps here to this x bar. So this is what it looks like. And so in this case, you can then afterwards, once you have this model here, which corresponds to this picture here, then you can contract again this component and also this component, and then it leads, so in this case you get a good reduction. So here's really something to do. It's a nice computation, but I think it's maybe everyone, since it's already so late in the afternoon, we have already seen so much detail, I spare you, but this is a good thing that we can maybe also discuss tonight in the sessions. Okay, so what do we want to do? Yeah? We suppose that we have, now we look at the strategy. So we get as a first obstruction for liftability. And this looks as follows. If you think of this picture, yeah, so if you compute the Artin-Schreier equation here for this component, it looks like this. That should be an Artin-Schreier equation, which has exactly the same genus as the Kummer equation that the curve defined by the Kummer equation here. And so we have seen in Stefan's talk, here we have only an Artin-Schreier equation only branched at this, or ramified at this point. And so this number of points, it needs to match this conductor, this 3 here. Yeah? So this is the first obstruction for liftability. So the points that you have in characteristic 0, they need, the ramification points that you have in characteristic 0, the number of them need to match the ramification in characteristic P. So okay, so now suppose we have a G-Galois cover in characteristic P, so this is denoted by the bars, and we choose some Y bar, some ramification point. Yeah? So it has decomposition group G Y bar, and then, well, we can just take the function fields here and complete. And so we get such an extension of local fields, GY bar Galois extension of local fields. And we have already seen this before. This GY is then an extension of a cyclic group before the prime to P by a P group. Okay. And as we have seen in the previous talk of Saito, we get here such a filtration of lower ramification groups, of higher ramification groups in the lower numbering. I'm sorry. I'm only considered the lower numbering in this talk. Well, let me just, it's exactly the same basically the same definition as we've seen in the previous talk, but let me just write it. So we define such a function I of sigma, and it's defined as follows. We take a uniformizing element here upstairs of L, and we check how such a group element sigma acts on it, and compute the valuation of the difference between the sigma pi L minus pi L. And then this higher ramification group GT, it's defined as all elements in the Galois group such that this number I is at least T plus 1. There are several ways of normalizing it, but let's just stick to this one. Of course, there's lots of properties one can show on these filtrations. We have written some in the notes, but I won't go into this here. So, okay. Using these numbers a sigma, we can define the Artin character of this extension of local fields, and it's defined as follows. If sigma is not the identity, then it's just minus this number I that I defined before, and otherwise, if sigma is 1, then it's just the sum of all the others. And with this normalization, putting this for this 1, then you can see that it's a class function. Meaning that if you change the sigma by a conjugate, then the value doesn't change. Okay, this is almost the same as the Swan character that we've seen in the talk of of Saito before. Namely, you just the difference between this Artin character and this one character is just that you need to subtract the character of the regular representation. So it's basically the same thing. And then we have this following theorem, Hasse-Arf, due to Hasse-Arf and Artin. It's a fact that Saito has also already cited in the previous talk. And this is that this Artin character, or it amounts to the same, it's really a character. It means there exists some vectors, finite dimensional vector space V plus an action of this finite group, so a representation, such that the character of this representation is exactly our Artin character. Okay. So now, what does this have to do with our lifting problem? Okay, so this now we come to this necessary condition. Now suppose that the cover that we've chosen, it lifts to characteristic 0. Okay, so that means there exists some y to x, such that if I reduce it back, I get exactly the cover that I fixed. And we should have, okay, should be that, of course, this generic fiber, that this between is a cover of a G-Gawa cover of smooth projective curves. Okay, then we have the following theorem, so-called Bertin obstruction. Yeah, in this situation where this F lifts, and if we have some ramification points of the special fiber, then there should exist some finite set, delta, on which this group acts, such that if I take the character, I mean, of course, so I have this delta on this xg, this gives me a representation, and if I take the character of this representation, then I should get up to some factor coming from character of the regular representation, I should exactly get this Artin representation. Okay, so how can you see this geometrically? Well, let me just come quickly back to my example. Yeah. So suppose that we had this cover here, this Artin-Schreier cover, y to the power p minus y is x to the power 3. We have seen it lifts to characteristic 0 because that's the way we constructed it. Yeah, I mean, it's just you take this cover with A is P, and that's the lift. So now, what you can take, you can take the 4 points, the 4 branch points of this cover, the lifts of these 4 points, yeah? And on this, of course, G acts, well, it just fixes all of them. And if you take the character of that representation, it gives you exactly the Artin character of this Artin-Schreier character. And so this the way you should see this obstruction, this Bertin obstruction, say that, okay, well, it should be able to match these points in characteristic 0 with the points in characteristic P, so that for this cover and all the subcovers, it works out with the genus formula. It's basically the way you should see this obstruction. So it's a very rough thing, but it's already very helpful. It already rules out lots of things that cannot happen. So let me just do some more examples. So we have seen, first example, in this example B, which was the one that I showed you just before, with the Kummer equation given branched at 4 points. There you just take as a delta set just 4 points, which all fixed by G. Cyclic group of order P, and Okay, so of course it's a lot of work to really check that this thing works. You need to work out the character and stuff, but this is exactly what it says in this case. That this is just what you have to do. Okay. So let me just look at the condition that Stefan discussed in his talk. Yeah. So we had as a group this extension of Z mod MZ by cyclic group of order P. And okay, let's just already assume that we know that the character is injective. Okay, so we look at special covers which are of this Katzgabber type to have one totally branched point and one tame point. So in this case, this Bertin obstruction says that this conductor, this H, the conductor of this, this was this H that Stefan had in his talk. The top step is an Artin-Trier cover. That's where this H comes from. And so you can see it as follows, yeah, because you have this in this case. And so we have in characteristic P, we had such this cover. This was the P step. This was the Z mod M step. And now you suppose that we could lift this to characteristic 0. Just and then here we should have H plus 1 branch points of this step in order that the genus maps. But here on these points, Z mod MZ should act, and it cannot fix any points. So that's where this condition comes from. It cannot fix any points because then we would have a stabilizer that's not cyclic, and it cannot happen here. So this is exactly what you get in this case. Right? It's exactly what Stefan said. He said it was. He said he gave a different way of you could see it, but this is how the Bertin obstruction tells you to do it. One more example. Let's look at Q8. So we take the quaternion group of order 8, and we suppose that we are in characteristic 2. And I consider a class of such quaternion actions. So I consider now conductors H of the form 1 plus 2n for some n. And what you can show, this is an exercise in our notes, but I don't think it's so helpful now to write down these equations here. So if you take this Artin-Trier curve, y squared plus y, I mean, you could write minus here also, we're in characteristic 2, doesn't matter. Y squared plus y is x to the power minus h. Then you can show, actually, it's a result of, or it was known before, but this is an example that I took from a paper of Lehr and Matignon, that on this you can define an action of the group Q8. So, I mean, you have to work a little bit to really write it down, but you can do it. It's elementary in some sense. I mean, I sketched it in the notes how you can do it. So you have to believe me on this, that this curve admits an action of G8. And what you also can show, this is the first thing you can show, and the second thing, you can then actually compute the filtration of higher ramification groups. And it's a very easy filtration. So it's a two-step filtration. So in the first two steps, you have the full quaternion. Then it jumps to a cyclic group of order 2. It's just given by the center, which I denote by minus identity. This is the center of the quaternion group. And then it just stays there until this integer h, and then it drops to 0. So it's just a two-step filtration. Okay, and now this is exercise 4.7 in our notes. You compute that this Bertin obstruction vanishes. I mean, you can do it exactly in the same way that I analyzed this example here. you can really say, okay, I have this subcover. I first have the degree 2 cover, corresponds to this case. Then I have this other part. The quotient is a Klein 4 cover. What should your genus be? And you can deduce from this exactly how the genus of the two steps should be. And then you see how it, whether it's possible or not. Yeah, so it's really explicit in some sense. I don't want to do it here, but it's really an explicit computation, which is exactly the same like the thing I did here. Okay, so the Bertin obstruction vanishes if and only if h is congruent to 1 modulo 4. And since h is given by 1 plus 2 to the power n, this happens if and only if there's only one case where it doesn't vanish, namely n is 1, and as soon as n is at least 2, of course it vanishes. Okay, so let's look in the last 15 minutes. Let's look a bit more detailed in these examples, and then you can see really what you have to do to see this. So let's look at two special cases. So let's first look at the case that h is 3. So this is the case that the curve, maybe I should just write this general picture again. So this family was constructed in such a way, let me just explain this a little bit more detailed, that if you take the quotient of this curve, I mean this still works for arbitrary h. So it's first you have a degree 2 cover here of a projective line, and then here you have of course then a degree 4 cover. So here this Galois group here is the center of the quaternion groups, just Z mod 2Z or minus identity. And then the quotient of the quaternion group by the center is just a Klein 4 group. And here, what you get is just this, in this case, the way I chose my family is that this Klein 4 group is just P1 to P1. And, well, you all maybe know that there is a unique, in any characteristic, you have such a unique Klein 4 group cover of P1 to P1. It's easy to write down. So this part actually is also easy to lift to characteristic 0. It's also uniquely liftable. It's just also the PSO2R, for example, has a subgroup isomorphic to Klein 4 group, and that's just the cover that you get if you lift this. So there's no, but now the point is how can you do this? Yeah. So in this case where you have h equal to 3, and this is an elliptic curve. I mean, of course, we know in characteristic 2, supersingular elliptic curve admits an automorphism, a subgroup, the automorphism group admits Q8 as a subgroup. So this is the supersingular elliptic curve, in fact. But then you know that if you look at Silverman, the book of Silverman, there's a list of automorphism groups of elliptic curves, and Q8 is not there. So there's no elliptic curve in characteristic 0, which admits Q8 as an automorphism group. So no way this guy is going to lift. Okay, but that's also what our Bertin obstruction says. So, but you can now see this really from the Bertin obstruction. So if you would lift this step to characteristic 0, it lifts to P1 to P1, which has 3 branch points. So suppose, let's just do the proof again, but just using now this Bertin obstruction. Suppose it lifts, then the lift would look like this. And here we have this Klein 4 cover. It has 3 branch points, there's no choice, so it has 6 ramification points here. But then this step, it's a degree 2 step, it's a Kummer equation, and since this should be an elliptic curve, this should be, here we should have 4 branch points in this step. In this step we have 6 ramification points, but here we have 4 branch points, but we know that every element here in the Klein 4 group, it lifts to an element of order 4 in the quaternion group, and so it should be, all these 6 points should be branched in total. okay, no way this is going to work. So this is the kind of obstruction. This is the kind it says. All the 6 points should be branched also in this cover due to the group, the way the group is constructed, but the genus, the number of branch points don't match up. So that's what it says in this case. Now I have a few more minutes, so I can do one more special case. Now let's look at the case H is 5. So in this case, the genus of Y2 is 2. Okay. So in this case, I already told you the Bertin obstruction does not vanish. It does vanish, I'm sorry. So in this case, you still have here, I mean, it would look exactly the same. Here you lift this, here you have 6 ramification points, and then here you have also 6 ramification points. That's the way the numbers work out here. Okay, and that's just, 5 plus 1. Yeah? So you see okay, so it's possible. Yeah, that's just what the Bertin obstruction says. Okay, we have the right amount of branch points. We can make our set delta in such a way. We just take this tells us how we should take the set delta and how the group should act on it. That's exactly what it tells. That Bertin obstruction vanishes, but still, we cannot lift this cover from characteristic P to characteristic 0, namely. So I'm going to explain you now why this is the case. This cover does not lift. And the reason is as follows. I mean, there is a result of Ikusa, an old result from the 50s, which tells you the automorphism groups of curves of genus 2. Okay, you look in the list, you find your quaternion, and it turns out in characteristic 0, there is a unique curve, Y, which contains Q8 as a subgroup of the automorphism group. Namely, which one is it? It's the one that I had in example A. It's given by this equation. I mean, here it's also in the notes, write down the automorphisms. It's not so bad. You can really do it. So here on this curve we have the Q8 acting. Yeah, but we have already. So this is our. If this curve lifts, then the lift should be this Y. This should be our Y because it's the only one. Okay, but we have already seen that this curve. We have already seen that this curve, if I reduce it back to characteristic 2, you get these 2 elliptic curves and not just a genus 2 curve. Yeah? Okay, so let me just go back to that picture. Yeah. So the reduction of this is the reduction of the curve Y of this equation. And so we see, well, it could not, this guy cannot be lifted because the lift would be this, and this reduces to this. And it's not the smooth cover that we want. So what you can see from this, the Bertin obstruction tells you only very, very first information. It tells you, okay, can we find the right amount of points with the right action on the group that could possibly be? But you see from this example that in order to really have then good reduction, these points should be in a certain configuration. The relative position, the same what we saw in this Kumar example with the 4 points. In order for this curve to have good reduction, the points should be adjusted in such a way that they reduce exactly to the same thing that we would end up with this cover. And the Q8 action just forces them to be in the wrong position. And therefore, this curve cannot have good reduction. So that's basically, so we see, we need more subtle information to see which curves can actually be lifted. And this is then going to be this differential form that Stefan introduced at the end of his talk, so-called differential data. This is additional data given such a, for example, this cover in characteristic P, we have to see that we can make a tree with additional data. And that then helps us to lift the cover. And in this special case, it turns out you cannot put for this curve, that does exist. I wrote it down, the Kummer equation, curvature CP, it does exist. You cannot put the right differential data, and that gives then another proof why you cannot lift it. So this is sort of the strategy. So what I'm going to do in the next talk, we're basically I mean Q8 is already of course a complicated group. It's a non-abelian P group. So there to define these differential forms and so on, it's rather complicated. I'm not going to do it in the talk. We restrict to the case that P strictly defines the order of the group, but I will. But you have seen in this example, that's exactly why I chose it, to compute the stable reduction of this cover, we could reduce to this, to this cover here, which is a degree 2 cover where we can apply our methods, and that was actually enough for this example. So that's why that's the thing we're going to do. Okay, thank you very much.